Close your eyes and imagine looking up on a perfect afternoon, watching as white shapes drift slowly overhead. Let us begin our journey into the sky, where water writes poetry across the atmosphere. These aren't just simple puffs of vapor, they're ancient travelers, carrying stories written in droplets and ice. Every cloud you've ever seen began with something impossibly small. A single cloud droplet measures only about 10 micrometers across. That's 100 times thinner than a human hair. To put this in perspective, you could line up 2,500 of these droplets side by side, and they would barely stretch across the thickness of a credit card. These microscopic spheres are so tiny that millions of them must come together before your eyes can even detect their presence in the sky. But here's something remarkable. These droplets cannot form from pure water vapor alone. The atmosphere needs help, needs tiny anchors floating through the air. Dust particles, sea salt crystals, even pollen grains, these become the seeds around which water vapor condenses. Scientists call them cloud condensation nuclei, and without them, our skies would remain largely empty. The air around you right now holds thousands of these invisible seeds in every breath you take, waiting for the right moment to birth a cloud. As water vapor rises and cools, it clings to these particles and slowly, so slowly, a cloud begins to form. The average cloud droplet contains about 1 billion water molecules, all held together in a delicate sphere by the invisible hand of surface tension. Think of it, 1 billion molecules, just to create something you still cannot see with your naked eye. Only when countless billions of these droplets gather together does the cloud finally reveal itself against the blue. And what you see when you look up is, in truth, closer to you than you might think. Most of the clouds that decorate our everyday skies, those fair-weather cumulus clouds that look like cotton balls, float between about 3,000 and 6,500 feet above the ground. That's roughly the height of 4 to 10 Empire State Buildings stacked on top of each other. Close enough that on a mountain hike, you might actually walk through one, feeling its cool kiss on your skin as the world turns gray and soft around you. These lower clouds are travelers, but not rushed ones. A typical cumulus cloud drifts across the sky at roughly 10 to 20 miles per hour, about the speed of a leisurely bicycle ride through the countryside. Stand still and watch one for just a few minutes, and you can see its journey across the heavens, the way it shifts and changes, never quite the same from one moment to the next. Because clouds are not static things. They are constantly being born and constantly dying, even as they appear to float peacefully overhead. The average cumulus cloud has a lifespan of just 10 to 15 minutes. In that brief window, it rises, takes shape, casts shadows on the earth below, and then dissolves back into invisible vapor. The cloud you were watching moments ago is already a different cloud, reformed from new droplets, reshaped by invisible currents of air. Inside each cloud lives a hidden world of motion. While the cloud itself might drift slowly across the sky, the air within it churns and rises at speeds up to 22 miles per hour in smaller cumulus clouds, and even faster in their larger cousins. These invisible updrafts are the cloud's heartbeat, constantly pulling in moist air from below, feeding the droplets, sustaining the visible form you see from the ground. And yet, despite all this activity, despite containing millions upon millions of water droplets, clouds are surprisingly light. The water content in a typical fair-weather cumulus cloud, one of those small, fluffy clouds you see on a pleasant day, weighs about the same as an elephant, roughly 1,100 pounds. But this weight is spread across such an enormous volume of air, distributed among so many billions of tiny droplets, that it floats effortlessly, suspended in the atmosphere like a thought suspended in the mind. This is where our story begins, with these gentle clouds of daytime, the ones that taught humanity to dream. In our next moments together, we'll climb higher into the atmosphere, where clouds take on stranger and more magnificent forms. As we drift upward in our minds, leaving those friendly cumulus clouds below, the air grows thinner and colder. Here in the middle realm of the troposphere, we find clouds that stretch across the sky like vast sheets of gray silk. These are the Stratus clouds, the quiet ones, the clouds of overcast days and gentle mists. Stratus clouds form a blanket that can extend horizontally for hundreds of miles, yet they are remarkably thin, often just 1,000 to 1,500 feet deep from bottom to top. Imagine a layer cake stretched across an entire state, but only as tall as the empire. State building is high. This thinness is their signature, allowing them to cover the sky in gray without the drama of storms, creating that soft, diffuse light photographers call the perfect natural softbox. These clouds hang low, typically between 2,000 and 6,500 feet above the Earth, sometimes even lower. When stratus clouds touch the ground itself, we simply call it by another name, fog. They are the same thing really, the same suspension of water droplets in air. The only difference is where you stand in relation to them. Walk through fog and you're inside a cloud, look up at stratus and you're gazing at fog that never descended. But let us climb higher still, up to where the air grows cold enough to change everything. At altitudes above 20,000 feet, water can no longer exist as liquid droplets. Here, clouds are born from ice, each tiny crystal forming around that same dust or salt particle, but now freezing into geometric perfection. These are the cirrus clouds, those delicate wisps and mare's tails that streak across the highest reaches of the troposphere. Cirrus clouds live in the realm of permanent cold, at altitudes between 20,000 and 40,000 feet, high enough that commercial airplanes often fly through them. At these heights, temperatures plunge to -40 degrees Fahrenheit or colder, cold enough that water vapor transforms directly into ice without ever becoming liquid first. This process, called deposition, creates clouds made entirely of ice crystals, each one a tiny frozen masterpiece. And these ice crystals catch the light in ways water droplets cannot. When the sun sits low on the horizon, cirrus clouds can glow with brilliant oranges and pinks for up to an hour after the ground below has fallen into shadow. They are the last to say goodnight to the sun and the first to greet it at dawn, painted in colors that make poets reach for inadequate words. The wind at these heights moves with purpose and speed. Cirrus clouds can race across the sky at speeds exceeding 100 miles per hour, carried by the jet stream, those rivers of fast-moving air that flow around the planet like currents in an ocean. Watch a cirrus cloud on a clear day, and you might notice how quickly it changes, how it stretches and dissolves, rewriting itself across the blue in a matter of minutes. Here's something that seems impossible. Despite their ethereal appearance like brush strokes on the sky's canvas, cirrus clouds can be incredibly extensive. A single cirrus cloud system can cover thousands of square miles, creating a veil so thin you can see the blue sky through it, yet so vast it could blanket several states at once. They are the whisper of water in the atmosphere, barely there, yet everywhere. And they hold far less water than their lower cousins. While that cumulus cloud we met earlier weighs as much as an elephant, a comparable volume of cirrus cloud might weigh only as much as a large dog, perhaps 50 to 100 pounds of ice crystals suspended across an enormous space. They are more suggestion than substance, more light than matter, the ghosts of the atmosphere. These high ice clouds play a curious role in Earth's temperature. Unlike lower clouds that reflect sunlight and cool the planet, cirrus clouds act more like a blanket, trapping heat that radiates up from Earth's surface. They can warm the planet even as they beautify the sky, a reminder that beauty and consequence often intertwine in ways we don't expect. Let us rest here for a moment, floating in imagination among these ice crystal clouds, where the air is thin and the view extends for hundreds of miles in every direction. Soon we'll explore the giants of the sky, the towers that build themselves into the stratosphere, but for now, breathe slowly and picture these delicate cirrus wisps painting the upper atmosphere with ice and light. Now let us turn our attention to the giants, the architects of weather, the clouds that build themselves into towers reaching towards space. These are the Cumulonimbus clouds, and they are among the most powerful forces in our atmosphere. A mature cumulonimbus cloud can tower over 40,000 feet into the sky. That's more than 7 miles high, tall enough that if you stacked Mount Everest on top of itself, it still wouldn't reach the top of the tallest thunderheads. Some exceptional storms have been measured reaching heights of 60,000 to 70,000 feet, punching through the troposphere and into the stratosphere above, creating that characteristic anvil shape as they spread out against an invisible ceiling. These giants are born from warmth and moisture. On a hot summer afternoon, the sun heats the ground, which heats the air directly above it. This warm air, now lighter than the cooler air surrounding it, begins to rise like a hot air balloon. If conditions are right, if there's enough moisture, enough instability in the atmosphere, this rising air doesn't stop at a few thousand feet. It keeps climbing, building upward, drawing more warm air from below, creating an engine of vertical motion that can become truly extraordinary. Inside a mature cumulonimbus cloud, the updrafts that gently lifted our small cumulus clouds become raging rivers of air. These vertical winds can reach speeds of 100 miles per hour or more, powerful enough to keep hailstones suspended in midair, cycling them up and down through freezing and melting layers, coating them in ice like a pearl forming in an oyster. The strongest supercell thunderstorms have recorded updrafts exceeding 170 miles per hour, faster than most hurricanes. The amount of energy contained in a single large thunderstorm is almost beyond comprehension. An average thunderstorm releases energy equivalent to a 20-kiloton nuclear bomb, about the same power as the weapon that destroyed Hiroshima. But this energy is released slowly, over the course of an hour or more, dissipated through lightning, rain, hail, and wind, rather than in a single catastrophic instant. 10 such storms happening simultaneously around the world is not unusual. The Earth experiences approximately 1,800 thunderstorms at any given moment. And with this energy comes light. Lightning is the cloud's way of balancing electrical charges that build up from all those water droplets and ice crystals colliding within the turbulent interior. A single lightning bolt can heat the air around it to temperatures of about 50,000 degrees Fahrenheit, 5 times hotter than the surface of the sun. This sudden heating causes the air to expand explosively, creating the sound wave we call thunder, which can be heard from up to 12 miles away under ideal conditions. But not all of a cumulonimbus cloud's water falls as rain. These towering clouds are remarkably efficient recyclers. Scientists estimate that for every 10 droplets lifted into a thunderstorm cloud, only one actually makes it to the ground as precipitation. The other 9 are cycled back up by those powerful updrafts, evaporated back into vapor, or swept out the sides of the cloud to dissipate in the drier surrounding air. The cloud gives back most of what it takes, keeping its water in circulation like a beating heart keeps blood moving. A mature thunderstorm cloud can contain as much as 275,000 tons of water at any given moment. That's roughly the weight of 2,000 blue whales, all suspended in the air through the sheer force of rising wind. And yet this massive weight is constantly in motion, rising, falling, freezing, melting, a churning system of organized chaos contained within those dark gray walls. The lifespan of a thunderstorm cell tells its own story. Most individual cells live for only 30 to 60 minutes, going through a predictable life cycle: birth, maturity, and dissipation. They grow from that first warm updraft, reach their peak when rain begins to fall and create downdrafts that fight against the rising air, and finally dissolve when the downdrafts win, cutting off the supply of warm, moist air that feeds the storm. Some storms, though the organized ones, the supercells, can last for several hours, constantly regenerating themselves as long as conditions remain favorable. These are the clouds that shape our weather, that water our crops and fill our rivers, that remind us we're small. And yet even in their power they follow the same basic principles as that gentle cumulus cloud we met at the beginning of our journey: water vapor, condensation, nuclei, rising air, and time. The difference is merely one of scale and energy, of how much warmth the earth can give to the sky. Let us descend now from those towering giants and explore the spaces between, the middle layers of sky where clouds take on forms both familiar and strange. Here we find the alto stratus and alto cumulus clouds, living in that transitional zone between 6,500 and 20,000 feet above the earth, high enough to be cool, low enough to still hold liquid water. The prefix alto means high, though these clouds occupy the middle realm of our atmosphere. Alto stratus clouds appear as gray or blue-gray sheets that often cover the entire sky, thick enough to obscure the sun but thin enough that you can sometimes see its position as a lighter area, like a lamp behind frosted glass. These clouds often arrive as harbingers, appearing 12 to 24 hours before a storm system moves in, quietly announcing that weather is about to change. What's remarkable about these middle-level clouds is their composition. Between 6,500 and 20,000 feet, the temperature hovers around the freezing point of water, creating a strange state where clouds can contain both liquid water droplets and ice crystals simultaneously. Scientists call these mixed-phase clouds, and they represent a delicate balance, a momentary coexistence of two forms of water that wouldn't seem possible. The water droplets exist in a supercooled state, liquid even though the temperature is below 32 degrees Fahrenheit, until something disturbs them. Altocumulus clouds, the cousins of Stratus, arrange themselves in patterns that have captivated observers for centuries. These mid-level clouds often form in rows or waves, creating what looks like a textured ceiling across the sky. The individual cloud elements in an altocumulus formation are typically larger than your thumbnail when you hold your hand at arm's length. This simple test helps distinguish them from the higher cirrocumulus clouds, whose elements appear smaller than a thumbnail at the same distance. Sometimes these altocumulus clouds organize themselves into one of nature's most beautiful atmospheric displays, the mackerel sky. Named for its resemblance to the scales of a mackerel fish, this pattern occurs when atmospheric waves create regular ripples in the cloud layer, spacing the clouds in parallel rows. Sailors have long known this pattern, captured in the old weather saying, mackerel sky, never long wet, never long dry, a recognition that such skies often indicate unsettled weather ahead. The waves that create these patterns are gravity waves in the atmosphere, similar in principle to the ripples that spread across a pond when you toss in a stone. But in the sky, these waves can extend for hundreds of miles, invisible except where moisture condenses along their peaks, making the pattern visible. The spacing between the cloud rows often measures between 1 and 2 miles, creating a regular geometry written across the heavens. Another phenomenon of the middle sky deserves our attention, the cloud known as virga. This is precipitation that falls from a cloud but evaporates before reaching the ground, creating dramatic curtains of rain or snow that hang in midair like ghostly veils. From the ground, you can see these streaks extending downward from the cloud base, often appearing as dark wisps against a lighter sky. The rain is real, it falls, it exists, but the air below the cloud is so dry that every droplet evaporates in its descent, returning to invisible vapor before completing its journey to Earth. Virga reminds us that the atmosphere is layered not just in temperature and pressure, but in moisture. A cloud can exist in one layer where humidity is high, while just below it the air is parched and hungry for water. Between 30 and 40% of all precipitation that falls from clouds never reaches the ground. It returns to vapor somewhere in that journey downward, recycled back into the atmospheric system. The sky gives and takes in the same breath. These middle-level clouds also create some of the most stunning optical phenomena. When the sun or moon shines through a thin veil of altostratus or altocumulus composed of ice crystals, it can produce a corona, a series of colored rings around the light source. The corona occurs when light diffracts around the tiny ice crystals or water droplets, with different colors bending by different amounts. The innermost ring appears bluish, surrounded by rings of green, yellow, and red, creating a soft halo that seems almost dreamlike. The size of the corona tells us something about the cloud. Smaller droplets or crystals create larger coronas, while larger particles create smaller, tighter rings. It's as if the cloud is revealing its inner structure through light, allowing us to see not just its form but its composition, written in circles of color around the sun. There are clouds that exist at the very edges of what we can see, clouds so rare that most people will never witness them in their lifetime. These are the clouds that form beyond the realm of weather, in the highest reaches of our atmosphere where the air is so thin it barely exists at all. Noctilucent clouds appear in the mesosphere at altitudes between 47 and 53 miles above the Earth's surface, so high that they float above 99.9% of Earth's atmosphere. At this height, the air pressure is less than 1/millionth of what it is at sea level, a vacuum so profound that these clouds shouldn't exist at all. And yet they do, forming from ice crystals so small they make ordinary cloud droplets seem gigantic, crystals only about 100 nanometers across, roughly 1,000th the width of a human hair. These highest of all clouds can only be seen during twilight, in the deep summer months at latitudes above 50 degrees north or south. They appear as electric blue or silver wisps against the darkening sky, glowing long after sunset because they're so high that sunlight still reaches them even when the ground below lies in darkness. The name noctilucent means night shining, and watching them is like witnessing a secret, the atmosphere revealing something it usually keeps hidden. But let us return to the clouds of our everyday world, to the weather we can touch and feel. There's a particular type of cloud that appears before our eyes as if by magic on certain mornings, the lenticular cloud. These lens-shaped or saucer-shaped clouds form in the lee of mountains, hovering in place even as strong winds blow through them. They look so perfectly formed, so unnaturally smooth and stationary, that they've been mistaken for UFOs countless times. Lenticular clouds are born from waves in the air, created when wind flows over a mountain barrier. The air rises up one side of the mountain, cools and condenses into cloud at the crest of the wave, then descends and evaporates on the other side. The cloud appears stationary because it exists only at that precise point where the wave crests and the air is cool enough for condensation. The wind blows through the cloud at perhaps 40 or 50 miles per hour, but the cloud itself doesn't move. It's constantly being created on its upwind side and dissolving on its downwind side, a sculpture carved from flowing air. Sometimes these lenticular clouds stack themselves in layers, one above another, creating what pilots call a pile d'assiettes, a stack of plates. Each layer represents a different wave in the atmosphere, and the whole formation can hover above a mountain range for hours, perfectly still while the world rushes through it. They are most common near mountain ranges like the Rockies, the Andes, or the Alps, where steady winds and stable atmospheric conditions allow these standing waves to persist. Now consider the humble fog, which we mentioned earlier as simply a cloud touching the ground. But fog comes in many varieties, each born from different circumstances. Radiation fog forms on clear, calm nights when the ground cools rapidly, chilling the air directly above it until water vapor condenses. This is the fog that fills valleys at dawn, that burns off as the morning sun warms the earth. It typically forms in layers just 3 to 12 feet deep, though it can grow thicker given enough time and moisture. Then there's advection fog, created when warm, moist air moves across a cooler surface, like when warm air from over the ocean encounters cold coastal waters. The famous fog of San Francisco is advection fog, rolling in from the Pacific as warm air meets the cold California current. This fog can be much thicker and more persistent than radiation fog, sometimes lasting for days, reducing visibility to mere feet, and transforming the familiar world into something mysterious and otherworldly. The thickest fog ever recorded reduced visibility to less than 2 feet, so dense that people reported being unable to see their own feet when standing upright. In such conditions, you exist in a sphere of visibility no larger than your arm span, isolated in whiteness, every sound muffled and strange. The world contracts to almost nothing, reminding us how much we rely on sight, how disorienting it is when the air itself becomes opaque. Fog can form with remarkable speed under the right conditions. When warm rain falls through a layer of cold air near the ground, evaporation from the raindrops can saturate the air almost instantly, creating what meteorologists call precipitation fog or frontal fog. One moment you're driving in rain with reasonable visibility. The next, you're enveloped in thick fog, the temperature having dropped just enough for the air to surrender its invisible moisture into the visible realm. There's a particular magic to standing inside a cloud, whether it's fog at ground level or the mist you encounter hiking through mountains. Everything becomes soft-edged and close. Colors mute, sounds change. You're breathing in the cloud, feeling it on your skin, walking through something that from a distance appears so solid and defined. It's a reminder that clouds are not things but processes, not objects but moments of transition, water constantly moving between its invisible and visible forms. Clouds shape not only our weather but our very perception of time and light. Consider how a cloudy day feels different from a sunny one, not just in temperature but in the quality of time itself. This isn't merely psychological. Clouds fundamentally alter how much solar energy reaches the Earth's surface. On a completely overcast day, clouds can block up to 90% of the sun's direct radiation, yet the world doesn't fall into darkness. Instead, we experience diffuse light, scattered and softened by billions of water droplets. This is why photographers cherish overcast days. The light wraps around subjects evenly, eliminating harsh shadows, creating what artists have valued for centuries. The cloud layer becomes a giant softbox, miles wide, transforming the sun's point of light into gentle illumination from the entire sky. But clouds don't just block light, they also reflect it back. Into space, Earth's clouds reflect approximately 20% of incoming solar radiation back to space before it ever reaches the surface. This reflection, called albedo, is one of the primary ways our planet regulates its temperature. Without clouds, Earth would absorb far more solar energy, and our world would be significantly warmer. Scientists estimate perhaps 10 to 15 degrees Fahrenheit hotter on average. Clouds are climate regulators, part of a vast system of checks and balances that keeps our planet habitable. Yet this relationship is not simple. As we learned with cirrus clouds, some clouds warm the planet by trapping outgoing heat. The net effect, whether clouds cool or warm, depends on their altitude, thickness, and composition. Low, thick clouds like Stratus tend to cool by reflecting sunlight. High, thin clouds like Cirrus tend to warm by trapping heat. The balance between these effects shifts constantly as clouds form and dissipate across the globe, creating a dynamic equilibrium that climate scientists are still working to fully understand. Let us turn now to the poetry clouds right across the sky in the form of contrails, those long linear clouds that form behind aircraft. When a jet engine burns fuel at high altitude, it produces hot exhaust containing water vapor and particles. This exhaust enters air that's typically colder than -40 degrees Fahrenheit, and the water vapor instantly freezes into ice crystals, creating a cloud. If the surrounding air is dry, these contrails dissipate within seconds or minutes. But if the upper atmosphere is saturated with moisture, contrails can persist for hours, spreading out to become cirrus clouds indistinguishable from natural ones. Some contrails can spread to become 20 miles wide, creating vast sheets of artificial cirrus that can cover thousands of square miles. Studies have shown that on days when air traffic is heavy and conditions are right, contrails can cover up to 0.1% of Earth's surface at any given time. They create their own climate effect, contributing to both day and night warming by trapping heat, a reminder that we humans have become unintentional cloud makers, writing our presence across the sky. Now imagine standing on a mountaintop as the sun rises, looking down at a sea of clouds below you. This is one of nature's most serene sights, you above the weather, the clouds stretching to the horizon like an ocean of white. From this vantage point, you can sometimes see the cloud tops as the dynamic surface they truly are, rippling and flowing, rising in some places and sinking in others, creating topography as complex as the landscape hidden beneath them. From above, clouds cast shadows on themselves, creating depth and dimension invisible from the ground. The top of a cumulus cloud in bright sunlight can be brilliant white, reflecting up to 90% of the light that strikes it, while the base appears dark gray or even charcoal because it's in shadow, receiving only scattered light. The same cloud, then, is simultaneously the brightest and darkest object in the sky, depending on where you stand and what angle you view it from. There's a phenomenon called a glory that appears when you look down at clouds from above with the sun behind you. It creates circular rainbow-colored rings around the shadow of your head or the shadow of your airplane. Each observer sees their own glory, centered on their own shadow, because the glory is created by light reflecting back from the cloud droplets in precisely the direction from which it came. It's as if the clouds acknowledge your presence, crowning your shadow with rings of spectral light. The colors in a glory are created by light waves interfering with each other after bouncing off cloud droplets. The droplets need to be remarkably uniform in size, typically between 10 and 30 micrometers in diameter, for the glory to appear. This uniformity tells us something about the cloud, that it formed under stable conditions, with droplets growing at the same rate, creating millions of nearly identical spheres of water. The cloud reveals its history through the light it bends. Clouds have accompanied humanity since our first moments of consciousness, and we have always sought meaning in their forms. But clouds also hold within them the memory of Earth's water, participating in a cycle so ancient it predates the earliest life on our planet. Every drop of water in every cloud has been cycling through the atmosphere for billions of years. The water molecule that condenses into a cloud droplet above you today might have fallen as rain on a primeval forest, might have been drunk by a dinosaur, might have formed part of an iceberg, might have flowed through countless rivers and oceans. Water is neither created nor destroyed in any significant amount. It simply changes form, moving endlessly between ocean, atmosphere, land, and living things. On average, a water molecule spends about 9 days in the atmosphere before falling back to Earth as precipitation. 9 days of freedom in the sky before returning to the surface, to soil, to sea, to stream. But this is only an average. Some molecules might circulate for weeks if caught in the right atmospheric patterns, while others fall within hours of evaporating. The atmosphere holds approximately 3,100 cubic miles of water at any given moment, suspended as invisible vapor or visible cloud, enough to cover the entire planet in 1 inch of rain if it all fell at once. Yet the atmosphere holds only a tiny fraction of Earth's water. If all the world's water were represented by a gallon jug, the amount in the atmosphere at any moment would be just a single tablespoon. Despite this seeming insignificance, this tablespoon is doing tremendous work, moving heat around the planet, creating weather, enabling life. Every time water evaporates, it absorbs energy. Every time it condenses into cloud, it releases that energy. Clouds, then, are not just water. They're also packages of transported energy, moving heat from warm regions to cold ones, from surface to upper atmosphere. Let us consider the clouds of tropical regions, where warmth and moisture combine to create some of the most dynamic cloud formations on Earth. In the tropics, the sun's energy is most intense and evaporation rates are highest. The result is an atmosphere rich with moisture, ready to condense into towering cumulus and cumulonimbus clouds that can reach their maximum heights of 60,000 feet or more. The tropical atmosphere's deeper warmth allows clouds to grow taller than they can in temperate or polar regions. These tropical clouds organize themselves into patterns visible from space. The intertropical convergence zone, where trade winds from the northern and southern hemispheres meet near the equator, creates a belt of clouds that encircles the globe. From satellites, this appears as a bright band of white, constantly shifting north and south with the seasons, following the sun's most direct rays. This cloud belt is one of the largest continuous features on our planet, visible proof of the atmosphere's global circulation. Within tropical regions, clouds can also organize into clusters called mesoscale convective systems, aggregations of thunderstorms that merge and persist for 12 hours or longer, sometimes stretching across areas the size of entire states. These systems develop their own internal organization, with new storms forming along their edges while older ones dissipate in the center, creating self-perpetuating weather factories that can travel hundreds of miles before finally exhausting themselves. The Amazon rainforest generates its own clouds through a process that seems almost magical. The forest transpires, releases water vapor through its leaves, so efficiently that it pumps approximately 20 billion tons of water into the atmosphere every single day. This moisture rises, condenses into clouds, and falls back as rain, sometimes within mere miles of where it evaporated. The forest, in essence, creates its own weather, its own clouds, recycling the same water again and again. Remove the forest and the clouds disappear. Without the clouds, the forest cannot survive. They exist in profound mutual dependence. Over the oceans, clouds take on different characteristics. Marine stratocumulus clouds form vast decks that cover approximately 20% of Earth's ocean surface at any given time, more area than all of North America. These low clouds form when cool ocean water chills the air directly above it, creating stable layers where clouds can persist for days or weeks. From space, these cloud decks appear as bright white blankets stretching for thousands of miles, reflecting enormous amounts of sunlight back to space and playing a crucial role in regulating ocean temperatures. Sailors have long read clouds as signs of coming weather, and their folk wisdom often contains meteorological truth. Mare's tails and mackerel scales make tall ships carry low sails. Those cirrus clouds and altocumulus patterns we discussed earlier often appear 24 to 48 hours before a storm system, giving sailors time to prepare. The clouds arrive first because they form at the storm's leading edge, where warm air is already beginning to rise and override cooler air, creating the first condensation at high altitudes. Another sailor's saying, "Red sky at night, sailor's delight, red sky in morning, sailor take warning." This observation contains real science. A red sunset means the western sky is clear enough for the setting sun's light to pass through and illuminate clouds to the east. And since weather in mid-latitudes generally moves from west to east, clear skies to the west suggest fair weather approaching. A red sunrise, conversely, means clear skies to the east with clouds illuminated to the west, suggesting those clouds will arrive soon. In the coldest reaches of our planet, clouds take on forms unlike anywhere else on Earth. Arctic and Antarctic clouds face conditions so extreme that they operate by different rules, creating phenomena that seem borrowed from another world entirely. Polar stratospheric clouds form in the stratosphere during the polar winter, at altitudes between 50,000 and 80,000 feet, far above the realm of normal weather clouds. These clouds require temperatures below -108 degrees Fahrenheit to form, conditions so cold they exist only in the perpetual darkness of polar night. When sunlight finally returns during spring twilight, these clouds glow with iridescent colors, mother-of-pearl sheens of pink, blue, green, and violet rippling across their surfaces in waves. They're hauntingly beautiful, yet they play a darker role. These clouds provide surfaces where chemical reactions occur that destroy ozone, contributing to the formation of the ozone hole above Antarctica. In the Arctic during winter months, diamond dust falls from seemingly clear skies. This phenomenon consists of tiny ice crystals forming directly in the air when temperatures drop below -40 degrees Fahrenheit and humidity is just right. The crystals are so small and fall so slowly that they seem to hover, glittering in any available light like suspended jewels. When diamond dust fills the air and the sun or moon shines through it, it can create sun pillars, vertical shafts of light extending above and below the light source, as if the sun has been stretched into a column reaching from horizon to zenith. These ice crystal displays can become even more elaborate. When the right types of ice crystals fill the air, typically hexagonal plates and columns, they can create a complex halo display. Rings around the sun or moon at 22 degrees and 46 degrees radius, bright spots called sundogs on either side of the sun, an arc over the top called a circumzenithal arc, and sometimes a complete circle of light passing through the zenith called a periarc. The whole sky becomes a geometry of light, all caused by ice crystals acting as tiny prisms, bending light at precise angles determined by their six-sided structure. But let us journey now to the edges where land meets sky in the form of mountain clouds. Mountains don't just create lenticular clouds, they also wear permanent cloud caps called orographic clouds. Some peaks remain shrouded almost continuously. Mount Waialae in Hawaii is covered by clouds approximately 335 days per year, making it one of the wettest spots on Earth with an average annual rainfall exceeding 450 inches. The mountain forces moist air upward, the air cools, condenses, and releases its moisture in an endless cycle. The mountain creates its own perpetual storm. The summit of Mount Washington in New Hampshire experiences cloud cover about 60% of the time, roughly 220 days per year. But these aren't gentle clouds. The mountain sits at the intersection of several major storm tracks, and clouds there often arrive with winds exceeding 100 miles per hour. The observatory on the summit recorded a surface wind gust of 231 miles per hour in 1934, a record that stood for decades. Being inside a cloud on that mountain means being battered by ice particles traveling at highway speeds, a reminder that clouds are not always the soft, gentle forms they appear from a distance. Mountains also create clouds through another mechanism. They heat differently than the surrounding air. During the day, mountain slopes warm faster than the free atmosphere at the same altitude, creating upslope winds that carry moisture upward. This often results in cumulus clouds forming over peaks during the afternoon, even when surrounding valleys remain clear. By evening, as the mountains cool, these clouds dissipate, creating a daily rhythm of cloud birth and death tied to the sun's passage. There's a particular type of cloud called a banner cloud that forms specifically on the lee side of sharp, isolated peaks. The Matterhorn is famous for its banner cloud, streaming like a flag from the summit. These clouds form not from the peak pushing air upward, but from a pressure difference. As wind splits around the sharp peak, it creates a zone of lower pressure on the downwind side. Air rises into this low-pressure zone, cools, and condenses, creating a cloud that appears to flow from the mountain like smoke, even though the wind is blowing the opposite direction. The cloud is anchored to the peak, constantly forming on one end and evaporating on the other. Consider, too, the clouds that form in the wakes of islands. As trade winds blow across tropical oceans and encounter an island, the air flows around and over it, creating von Karman vortices, spiral patterns of clouds that trail downwind from the island like water flowing past a stone in a stream. From satellites, these patterns are strikingly beautiful, two parallel rows of spiral clouds, alternating direction, stretching for hundreds of miles across the ocean. They reveal the invisible texture of the wind, made visible only where moisture condenses at the right altitude. Even individual ships can create clouds. Ship tracks appear as bright lines across marine stratocumulus cloud decks visible from space. The ship's exhaust provides additional condensation nuclei, those microscopic particles we discussed at the very beginning of our journey. With more nuclei available, the cloud forms more droplets, but each droplet is smaller. Smaller droplets reflect more light, making ship track clouds brighter than the surrounding cloud deck. A single ship's passage can leave a bright scar across the clouds that persists for hours, a visible signature of humanity's presence written in altered water droplets. As we near the end of our journey through the realm of clouds, let us consider the subtle ways they touch our lives beyond weather and beauty, how they've shaped human culture, navigation, and our understanding of the world itself. Before satellites and weather stations, clouds were humanity's only forecast. Indigenous peoples around the world developed intricate knowledge systems for reading the sky. The Maori of New Zealand recognized over a dozen distinct cloud types, each with its own name and meaning. They knew that certain cloud formations over the ocean indicated schools of fish beneath, that specific patterns foretold the arrival of storms days in advance. This wasn't superstition but empirical knowledge, accumulated over countless generations of careful observation. Clouds also served as navigators. Polynesian wayfinders crossing thousands of miles of open Pacific Ocean used clouds to find land they couldn't yet see. Stationary clouds that form over islands, those orographic clouds we discussed, can be visible from 50 miles away or more, appearing as fixed points against the moving sky. Even the color of clouds reflected clues. Greenish undersides might indicate reflection from a shallow lagoon, while darker undersides might mirror dense vegetation. The clouds became maps, written and rewritten daily by the atmosphere. In our modern world, clouds still guide navigation, but in different ways. Pilots rely on cloud types and patterns to avoid severe weather and turbulence. Smooth lenticular clouds, for instance, indicate severe turbulence in the mountain waves that created them. Experienced pilots give these clouds a wide berth. Mammatus clouds, those strange pouch-like formations that hang beneath the anvil of a cumulonimbus, often signal that a thunderstorm is particularly intense, though the mammatus themselves usually appear during the storm's dissipating phase after the worst has passed. Mammatus clouds form when pockets of cold air sink down from the cloud base, creating bulges that can extend several hundred feet below the main cloud deck. Each pouch typically measures 1 to 3 miles across, and fields of mammatus can cover hundreds of square miles, creating an upside-down landscape of hanging bulges that seem to defy gravity. They appear most commonly in late afternoon and evening, illuminated by the setting sun in shades of gold and amber, transforming the underside of the storm into something otherworldly. Let us speak now of the speed at which clouds can form. Under the right conditions, a cumulus cloud can grow from nothing to a fully formed cloud in just 10 to 15 minutes. You could be looking at a patch of empty blue sky, and by the time you've made a cup of tea and returned, a cloud has materialized where none existed before. This rapid formation occurs when a parcel of warm, moist air suddenly finds itself buoyant enough to rise rapidly, punching through the condensation level and continuing upward, building vertically as you watch. Conversely, clouds can dissipate with equal speed. As soon as the conditions that created a cloud change, if the air dries, if the updraft ceases, if sinking air warms the layer, the cloud begins to evaporate. The droplets return to invisible vapor and the cloud simply vanishes, leaving only blue sky where white forms existed moments before. This impermanence is essential to the cloud's nature. They are not objects but processes, not things but transitions, existing only as long as conditions support them. The total mass of all clouds in Earth's atmosphere at any given moment equals approximately 1.1 trillion pounds of water. That's roughly the same weight as 100 million elephants. This seems enormous until you remember that this mass is distributed across the entire planet, spread through millions of cubic miles of sky. The atmosphere is so vast that even this tremendous weight becomes almost negligible, a thin veil of moisture suspended in an ocean of air. Climate scientists have discovered that clouds are among the most uncertain factors in predicting future climate change. Small changes in cloud cover, cloud altitude, or cloud composition can have outsized effects on Earth's temperature, yet clouds respond to warming in complex ways that vary by region and season. Some computer models suggest that warmer temperatures will create more low clouds that cool the planet. Others suggest fewer clouds overall or a shift toward high clouds that warm it. This uncertainty means that clouds, those most familiar features of our daily sky, remain one of science's greatest puzzles. Recent research has revealed something unexpected. Clouds may play a role in the formation of rain that we didn't previously understand. Scientists have discovered that bacteria, fungi spores, and even particles from plants can act as ice nuclei, seeds around which ice crystals form, at temperatures warmer than dust or salt particles can. Some bacteria found in clouds appear to have evolved specifically to promote ice formation, perhaps as a strategy to return to Earth in rainfall. Life itself, then, may be helping to create the rain that sustains it, blurring the boundary between living and non-living systems. There's a particular quality to the light just before a storm arrives, when thick clouds approach but haven't yet covered the sun. The light takes on a strange intensity, colors become more saturated, shadows deepen. This happens because the approaching clouds create a darker background against which the still sunlit foreground appears brighter by contrast. Photographers call this storm light, and it lasts only minutes, that brief window when the world seems to hold its breath before the sky opens. As our journey through the world of clouds draws toward its close, let us explore some of the most mysterious and rarely seen cloud formations, and consider what clouds mean for the future of our changing planet. There exists a cloud so rare that it was only officially recognized and added to the International Cloud Atlas in 2017, despite being observed and photographed for decades. The Spiritus cloud, from the Latin word for roughened, appears as a dark, turbulent underside with chaotic, wave-like structures that seem to churn and roil across the sky. Unlike the organized waves of other cloud patterns, Spiritus looks almost liquid, as if the sky itself has become a stormy sea frozen in time. These clouds typically form in the aftermath of thunderstorms, in the boundary layer between different air masses, and they can persist for hours, creating an atmosphere of dramatic foreboding, even though they rarely produce severe weather. Another extraordinary phenomenon appears in the skies above thunderstorms, visible only from aircraft or satellites, sprites, jets, and elves. These are electrical discharges that occur in the upper atmosphere, triggered by lightning below but reaching upward towards space. Red sprites flash briefly 30 to 55 miles above large thunderstorms, lasting only milliseconds but extending tendrils down toward the cloud tops like jellyfish made of light. Blue jets shoot upward from cloud tops at speeds up to 60 miles per second, while elves, short for emission of light and very low-frequency perturbations from electromagnetic pulse sources, create expanding rings of light in the ionosphere. These phenomena remind us that clouds reach beyond their visible boundaries, affecting the atmosphere for dozens of miles above their highest ice crystals. In the Southern Ocean, one of the most remote and stormy regions on Earth, clouds behave differently than almost anywhere else. Here, far from continental landmasses and human pollution, the air is exceptionally clean, so clean that clouds sometimes struggle to form because there aren't enough condensation nuclei. Scientists have discovered that in this region, sea spray and particles from marine algae become crucial cloud seeds. The algae release sulfur compounds that oxidize in the atmosphere to create particles around which clouds can condense. The ocean, in essence, is seeding its own clouds, creating the very formations that will shade its surface and influence its temperature. Clouds also participate in the nitrogen cycle in ways scientists are only beginning to understand. Lightning within thunderclouds creates temperatures high enough to break apart nitrogen molecules in the air, allowing them to combine with oxygen to form nitrogen compounds. These compounds dissolve in rain and fall to Earth, where plants can absorb them as nutrients. It's estimated that lightning produces about 5 to 8 million tons of nitrogen compounds annually, a natural fertilizer factory operating in the sky, powered by the electrical energy of storms. Every thunderstorm, then, is not just water and light, but also part of the nutrient cycle that sustains terrestrial life. The highest cloud ever documented was a cumulonimbus that reached an altitude of 68,000 feet over the Pacific Ocean, more than 12 miles high, punching well into the stratosphere. At that altitude, the air pressure is less than 10% of sea level pressure, yet the storm's updrafts were powerful enough to carry air and moisture into this hostile environment, creating a cloud tower that could be seen from hundreds of miles away. Such extreme clouds are rare, requiring a perfect combination of atmospheric instability, moisture, and energy. As Earth's climate warms, cloud patterns are changing in subtle but measurable ways. Observations over the past few decades suggest that cloud tops are gradually getting higher, rising by approximately 100 to 130 feet per decade. This happens because a warmer atmosphere has more energy to drive stronger updrafts, allowing clouds to grow taller. The tropopause, the boundary between the troposphere and stratosphere where clouds typically stop growing, is also rising, giving clouds more vertical room to develop. Simultaneously, clouds appear to be shifting poleward. The zones of subtropical dry climate where clouds are sparse are expanding toward the poles by about 30 to 40 miles per decade. This shift pushes rain-bearing clouds toward higher latitudes, potentially altering rainfall patterns that entire civilizations have organized themselves around. Regions that have relied on seasonal rains for agriculture may receive less precipitation, while areas unaccustomed to heavy rainfall may experience more. The clouds are moving, and the weather map of Earth is being slowly redrawn. There's a concept in cloud physics called the Clausius-Clapeyron relation, which describes how warmer air can hold more water vapor before reaching saturation. For every 1.8 degrees Fahrenheit increase in temperature, the atmosphere can hold approximately 7% more water vapor. This means a warmer world will have a more moisture-laden atmosphere, and when that moisture condenses, it can produce more intense rainfall. The heaviest rain events, the kind that cause flooding, are becoming more common, not because there are more storms, but because each storm can carry and release more water. Yet even as we understand more about clouds, they remain unpredictable in their details. 2. Clouds that appear identical from the ground may have entirely different internal structures, different droplet size distributions, different ice crystal habits. Each cloud is unique, formed by a specific combination of temperature, humidity, pressure, and aerosols that will never be exactly replicated. In this way, every cloud that has ever formed in Earth's 4 billion-year history has been an original, a singular creation that existed briefly and then dissolved, unrepeatable. Perhaps this is what draws us to clouds, their combination of pattern and randomness, their adherence to physical laws while remaining infinitely variable. They are both predictable and surprising, familiar and strange, substantial and ephemeral. As we drift deeper into our understanding of clouds, let us explore the invisible architecture that supports them, and the delicate balance between what we can see and what remains hidden from our eyes. Within every cloud exists a hierarchy of motion at different scales. At the smallest scale, individual water droplets are constantly colliding with each other in a process called coalescence. When two droplets touch, surface tension pulls them together into a single larger drop. This happens billions of times within a cloud, and it's one of the primary ways raindrops grow large enough to fall. A typical raindrop that reaches the ground has formed from the merger of approximately 1 million cloud droplets, a million tiny spheres becoming one, heavy enough to overcome the updrafts and begin its descent. But this growth process is remarkably inefficient in clouds made purely of water droplets. In warm clouds, those entirely above freezing, it can take 30 minutes to an hour for droplets to collide enough times to form raindrops. This is why warm rain tends to be lighter and more prolonged. In contrast, clouds that contain both ice crystals and supercooled water droplets, those mixed-phase clouds we discussed earlier, can produce precipitation much more rapidly, often in just 15 to 20 minutes, because ice crystals grow more efficiently by stealing water vapor from the surrounding supercooled droplets. This process has a name, the Bergeron-Findeisen process, after the scientists who discovered it. Water vapor prefers to deposit onto ice rather than liquid water at temperatures between 0 and -40 degrees Fahrenheit. Ice crystals in a mixed-phase cloud essentially starve the water droplets, growing larger while the droplets evaporate. Once the ice crystals become heavy enough, they fall, sometimes melting into raindrops on their way down, sometimes reaching the ground as snow. Most rain that falls in temperate latitudes actually begins as snow high in the clouds, melting only in the warmer air below. Consider the variety of snowflake forms that can emerge from clouds. The shape of a snowflake depends primarily on the temperature and humidity at which it forms. At around 27 degrees Fahrenheit, crystals tend to form thin plates. At 23 degrees, they become columns. At 5 degrees, they develop into the classic six-branched dendrites we associate with snowflakes. Each branch of a single snowflake grows in the same environment, experiencing the same sequence of temperatures and humidity as it falls, which is why all 6 branches develop similar patterns. They're recording the same atmospheric journey. Yet no two snowflakes follow exactly the same path, which is why each one's pattern is unique. A single large snowflake might contain up to 275 separate ice crystals that have collided and stuck together during their fall, creating an aggregate larger and more complex than any individual crystal could become. In the right conditions, these aggregates can grow to extraordinary sizes. The largest snowflakes ever reliably recorded fell in Fort Keogh, Montana, in 1887, with some measuring 15 inches across, wider than a dinner plate. These giant flakes formed during a period of light winds and temperatures just below freezing, conditions perfect for crystals to stick together without breaking apart. Now let us consider what happens when ice crystals remain in a cloud too long, cycled up and down by powerful updrafts. Each time they rise into the coldest regions of the cloud and fall back through zones of supercooled water, they acquire another layer of ice. This is how hailstones form, growing like pearls, layer by concentric layer. If you slice a hailstone in half, you can count the layers like tree rings, each one representing another trip through the storm's vertical currents. The largest hailstone ever recorded in the United States fell in Vivian, South Dakota in 2010. It measured 8 inches in diameter and weighed nearly 2 pounds, about the size of a volleyball. For a hailstone to grow this large, it must remain suspended in a thunderstorm's updrafts for an extended period, perhaps 15 to 20 minutes, cycling through the cloud multiple times. The updraft speeds required to keep such a stone aloft must exceed 100 miles per hour. When it finally falls, it can plummet at speeds approaching 100 miles per hour as well, carrying enough energy to shatter windshields and punch through roofs. Yet even ordinary rain carries surprising power. A single raindrop, having formed from those million cloud droplets we mentioned, falls at a terminal velocity between 9 and 20 miles per hour depending on its size. Small drops fall more slowly because air resistance affects them more. Larger drops fall faster up to a point. Beyond a certain size, about 6 millimeters in diameter, raindrops become unstable. Air resistance flattens their bottoms, and they begin to oscillate and vibrate as they fall, eventually breaking apart into smaller drops. This limits the maximum size of raindrops and explains why rain comes in droplets rather than in streams or larger masses. The sound rain makes when striking surfaces has been studied extensively, revealing patterns most of us recognize intuitively. Light rain produces a soft patter of small drops hitting at intervals. Heavy rain creates a rush of sound as thousands of larger drops strike per second, merging into a continuous roar. The specific sounds, the ping on metal, the splash on water, the thud on earth, arise from the interaction between the drop's kinetic energy and the surface properties. We can hear the size of the drops and the intensity of the rain without seeing it, our ears translating falling water into information about the storm. There's a particular smell that arrives with rain after a dry period, a scent many of us cherish without knowing its origin. This smell, called petrichor, comes from oils that plants release into the soil during dry weather. When rain falls, it disturbs these oils along with a compound called geosmin produced by soil bacteria. The moisture releases these trapped scents into the air, where they reach our noses as that distinctive earthy aroma. The smell of approaching rain, however, that ozone-like scent before the drops arrive, comes from a different source. Electrical activity in the storm, which breaks apart oxygen molecules that recombine into ozone, carried to us on the storm's outflow winds. As we continue our gentle exploration, let us turn our attention to the ways clouds interact with light in some of nature's most spectacular displays, and how they serve as canvases for the sun and moon to paint upon. When the sun sits low on the horizon, just after sunrise or before sunset, its light must travel through a much greater thickness of atmosphere to reach our eyes, up to 40 times more atmosphere than when the sun is directly overhead. This long path causes the atmosphere to scatter away the blue wavelengths of light, leaving the reds, oranges, and yellows to illuminate the clouds. The most vivid sunset colors occur when there are clouds at mid to high levels to catch this light, while the lower atmosphere remains relatively clear. The clouds become screens onto which the filtered sunlight projects its warmth. But the most intense colors appear not in the clouds themselves, but in the spaces between them. When scattered clouds dot the sky at sunset, the gaps of clear air can glow with colors more saturated than the clouds, brilliant magentas, deep purples, electric oranges. This happens because the clear air scatters the colored light in all directions, filling the sky with color, while the clouds merely reflect it. The interplay between reflective cloud and glowing sky creates a complexity of hues that seems almost unnatural in its intensity. There exists a brief window of time, lasting only 15 to 20 minutes, when the sun has set below the horizon but its light still reaches high clouds. Meteorologists call this civil twilight, but photographers know it as the golden hour's softer companion, when light becomes diffuse and gentle, when high cirrus clouds can glow against a darkening blue sky. During this time, the quality of light changes by the minute, evolving from gold to pink to purple to blue-gray, a continuous transformation that repeats in reverse each dawn. Moonlight, too, interacts with clouds in ways worth contemplating. A full moon shining through thin cirrus clouds can create a lunar corona similar to the solar corona we discussed, rings of color surrounding the moon's disk. But moonlight is roughly 400,000 times dimmer than sunlight, which means these lunar displays appear more subtle, requiring dark skies and adapted eyes to appreciate fully. On a clear night with thin clouds and a full moon, the corona can appear as a soft bluish disk immediately around the moon, sometimes surrounded by faint reddish rings. When the moon is particularly bright and clouds are present, a phenomenon called moon bows or lunar rainbows can form. These are rainbows created by moonlight refracting through raindrops, following the same optical principles as solar rainbows but appearing much fainter. To human eyes, which see primarily in black and white at low light levels, moon bows often appear as pale arcs of white or gray. Only in long-exposure photographs or to exceptionally dark-adapted eyes do their colors become visible, ghostly versions of the vibrant arcs we see by day. Let us speak now of the green flash, one of the rarest and most sought-after optical phenomena involving the sun and atmosphere. Just as the sun's last sliver disappears below a clear horizon, or just as it first appears at sunrise, the top edge can briefly flash green for 1 or 2 seconds. This occurs because the atmosphere acts as a prism, separating the sun's light into its component colors. Red light bends least and disappears first, blue and violet scatter away, but green, being in the middle of the spectrum, remains visible for the briefest moment as the final color we can see. The green flash requires an extremely clear atmosphere and a sharp horizon. Ocean horizons are ideal, and clouds near the horizon will obscure it. Yet it remains connected to our story of clouds because the clarity of the sky, the absence of haze and cloud, makes the flash possible. Clouds themselves can produce colored lights under certain rare conditions. Nacreous clouds, also called mother-of-pearl clouds, form in the stratosphere at altitudes of 50,000 to 80,000 feet in polar regions, similar to the polar stratospheric clouds we discussed earlier. When the sun is just below the horizon, these clouds, still in sunlight because of their great height, can display brilliant iridescent colors that shift and flow across their surfaces. The colors come from diffraction, light waves bending around the tiny ice crystals, interfering with each other to produce pure spectral hues. These clouds are so rare that some meteorologists spend entire careers without seeing them. Cloud iridescence can occur in more common clouds as well, though it's subtler. When the sun shines through the edge of a thin cloud composed of uniformly sized droplets, colors can appear near the cloud's border, usually pastel shades of pink, green, and blue arranged in bands. This iridescence moves and changes as the cloud evolves, as different portions drift into the right position relative to the sun. It's easiest to see when the sun itself is hidden behind something, a building, a tree, so the bright solar disk doesn't overwhelm the delicate colors. On certain days when the sun shines through a very thin, uniform layer of cloud composed of ice crystals, the entire sky can seem to shimmer with subtle color. If you look carefully at areas of sky 20 to 30 degrees away from the sun, you might notice faint patches of red, green, or blue, appearing and disappearing as the cloud structure shifts. These are called irisation, and they reveal that even apparently uniform clouds have internal variations, regions where crystals are slightly more uniform, creating the conditions for color to emerge. The physics underlying all these optical effects is the same. Light is waves, interacting with particles and droplets of specific sizes, bending and scattering and interfering to create color where none existed in the particles themselves. The clouds don't contain color, they create it through their interaction with light, acting as instruments that translate invisible properties of sunlight and crystal structure into visible spectrum. And so we arrive at the end of our journey through the realm of clouds, though in truth, the journey never really ends. Every time you look up, the story continues, written anew in water and ice and light. Let us gather together what we've learned, not as a list of facts, but as an understanding. Clouds are not separate from us, but intimately connected to everything that makes Earth habitable. They are the atmosphere made visible, the water cycle given form, energy, and matter in constant conversation with each other. Every breath you take contains moisture that was recently part of a cloud. Every glass of water you drink has cycled through clouds countless times over Earth's long history. The rain that feeds the forests, fills the rivers, and sustains all terrestrial life falls from clouds following principles both simple and profound. Water vapor rising, cooling, condensing, and returning to the surface in an endless exchange. We've traveled from the smallest cloud droplet, 100 times thinner than a human hair, to the largest thunderstorms containing the weight of 2,000 whales. We've climbed from fog touching the ground to noctilucent clouds 50 miles high, shining in the darkness. We've watched clouds form in minutes and dissipate just as quickly. We've seen them persist for days as vast blankets over the ocean. And we've learned that each one is absolutely unique, unrepeatable, irreplaceable, a singular moment in the atmosphere's continuous evolution. Clouds regulate our planet's temperature, reflecting sunlight and trapping heat in a delicate balance that shifts with every formation and dissipation. They transport water from ocean to land, they carry heat from equator to poles, they generate the lightning that helps fertilize the soil. They create rainbows and halos, sundogs and glories, painting the sky with light transformed by ice and water into color. They are both ancient and newborn. The water in them has existed for billions of years, yet each individual cloud lives for minutes or hours, never quite the same from one moment to the next. They are massive yet weightless, powerful yet ephemeral, governed by immutable physical laws yet infinitely variable in their expression. Perhaps what draws us most to clouds is this very paradox. They are both knowable and mysterious. We understand the physics of their formation, can predict their behavior with increasing accuracy, can measure their properties with sophisticated instruments, and yet they remain fundamentally wild, spontaneous, impossible to control or fully predict in their details. They remind us that the natural world operates according to principles both orderly and creative, structured yet free. As you drift towards sleep, imagine yourself floating among them, not struggling against gravity but simply present, suspended in cool moisture and soft light. Feel the droplets on your skin, each one a tiny world unto itself. Hear the silence of the upper atmosphere, broken only by the rush of wind. See the earth far below and the blue dome of sky above, and know that you exist in the thin layer where water transforms between its states, where clouds are born and die in their endless cycle. Tonight and every night, clouds continue their work across the planet. They gather over warm oceans, build into towers over heated land, spread into sheets across entire continents. They drop rain on forests and deserts, snow on mountains and plains. They catch the last light of sunset and the first rays of dawn. They exist whether we watch them or not, following patterns established before humans walked the earth, patterns that will continue long after we're gone. But in this moment, in this quiet space before sleep, they are yours to contemplate, each cloud you've ever watched, each storm you've witnessed, each rainbow you've marveled at, all of them part of the same grand system, the same story of water and air and energy that makes our world what it is. Let the thought of clouds comfort you as you close your eyes. Somewhere above you right now, even if you cannot see them, clouds are forming and dissolving, drifting and transforming, doing the quiet work of sustaining the water cycle that sustains all life. They ask nothing of us except perhaps our attention, our wonder, our willingness to look up occasionally and remember that we live beneath a sky that is never quite the same twice. Rest now knowing that the clouds will be there tomorrow and the day after and always, ancient travelers carrying their cargo of water across the sky, writing poetry in condensation, telling stories in ice and light. They are patient teachers if we choose to learn from them, reminding us that the most essential things are often the most taken for granted, that beauty and function are not separate, that everything is connected in ways both visible and invisible. The clouds drift on through the night sky, and you drift too, into sleep, into dreams perhaps of floating among them, weightless and peaceful, suspended between earth and stars in the soft embrace of water vapor made visible, made beautiful, made into clouds.